All right, sequences, series, and convergence, divergence. So, starting this off, factorial. You might have to do this. The idea with factorial, if I say n factorial and this is n is some number, it must be an integer. You are multiplying every number down to 1, starting with that number and keep subtracting. So, like, if I had the number 5 factorial, this would equal 5 times 4 times 3 times 2 times 1. Or maybe let's start at 0 factorial. No, so 4 factorial will be like 4 times 3 times 2 times 1. This would be 3 times 2 times 1. This would be 2 times 1. 1 would just be 1. What's 0? Well, 0 is also 1. That's the rule for factorials. And it's not just multiplying those out. So 1 equals 1. 2 times 1 would be 2. This would be 6. This one's 24. And 24 times another 5 would be 120. I've done this before. The idea is you're multiplying every number down to 0. Factorials must be an integer, not a decimal. That doesn't work out. All right. So we use these. Sometimes we use these in patterns. You're going to see this as we talk about things like ratio test in this class. Sometimes sequences and series. If you do statistics like permutations, combinations. And feel free to stop me whenever you need to if I go too fast. So one of the things I might do, and before I do that example, what if I said, okay, not just numbers here. Wait, let's stop being weird. Let's not go straight to those examples. It's gonna make things up. So one of the things I might do in this class, I might try to like do some simplification. So what if I said something like 7 factorial over 5 factorial, and I wanted you to simplify this, all right? This is some good practice because we're going to have to do this kind of stuff. Well, let's write it out. 7 times 6 times 5 times 4 times 2 times 1. Is the times 1 even really matter? Not really. And this is 5 times 4 times 3 times 2 times 1. And then what cancels out? 3s, 4s, 5s. So what are you left with? 7 times 6, which is 42. So that's how you simplify this kind of stuff. And you might have to write it out and things will cancel. I can, it doesn't have to be top and bottom like this. What if I had 3 factorial over 5 factorial? It'd be 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. And you'd cancel out certain things, 3s, 2s, 1s. I'm left with 1 over 5 times 4 on the bottom, which is 1 over 20. Okay, might have to do this. Now, it's not always just numbers we do this with, and especially in calculus BC here, we're going to have to deal with like leaving it as n. So remember this formula. N factorial equals n times n minus 1 and times n minus 2, n minus 3, dot, 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 down to 1. So this is kind of like the generic if n is some integer. We might have to. What's the point? Oh, there's a. All right. The thing about these, so it's n factorial goes down. What if I said, what is n plus 1 factorial? Well, this would be n plus 1 factorial times 1 less than this. So it would be times an n, and then times an n minus 1, times n minus 2, dot, 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 all the way down to 1. That's typically how we represent that if we have to write things out. Now, why is that important? Because I might give you a problem like this. Let's say I wanted to simplify this math. And yes, this will come up when we talk about ratio tests and stuff later. How do I simplify this? Well, n minus 2. Let's write out n minus 2. It'd be n plus 2 times an n plus 1 times an n times n minus 1, dot, 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 down to 1. N factorial is going to be n times n minus 1 times n minus 2, dot, 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 down to 1. So I expand those out. Now I'm going to cancel things. So what cancels? N's. All this stuff cancels. So all I'm left with is an n plus 2 times an n plus 1 on top. That would be my simplified answer. All right. So you might have to do this with numbers. What I want you to do is I want you to try this and I will go over the answers. Or I want to do some of this. So if you expanded this out. Hopefully. That's how we play the cancel game. Left with 5 times 4 on top. And I can even reduce that to 10. Maybe you get the top one, you get a 10. Try the bottom one. Canceling everything. This is all going to cancel out. You're left with 1 over n plus 1 times n on bottom. The last one, oh, you're like, oh, this looks weirder. It's like 2n, right? Yeah, it's still do the subtraction thing. So it's like a 2n plus 1 times 2n minus 1, dot, 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 down to 1. We have 2n plus 3, 2n plus 2, 2n plus 1, down to 1. What's going to cancel out is all the 2n plus 1s. Maybe you start seeing the pattern in here. You don't need to write out as much. But this stuff's going to happen. Just want you to get used to factorials right here. Right. Moving on. So other things that are happening in here, a sequence. When we talk a sequence, it's a list of numbers. So a sequence is a list. So a sequence could be like 1, 3, 5, 7, 9. That's a sequence of numbers. We're not doing math, it's just a list. So it could be, doesn't have to start at 1. It could just be like 25, 5, 1, 1/5, etc. Typically for sequences here, there's going to be some kind of pattern to these things. So, and if you look at this pattern on top, what am I doing? You might say, oh, I'm adding 2 every time. And what am I doing down here? Oh, I'm dividing by 5 every time. And then 1/5 is dividing by 5 again. You might say, well, what's my next one would be 1/25. The next one in this sequence would be 11. So if we had like an infinite sequence going on forever. Sometimes the pattern is told to you, or sometimes you have to infer it or I give you like the formula. I'll give you the formula for these kind of things. And you'll see how this evolves. Sometimes you need to figure out the pattern. I know this feels very pre-calculus, but I might give you a problem like this. So if I asked you write out the first 5 terms of the sequence, yes, this is very pre-calculusy. Sequence A of n. So I might say for the formula, I might give you, this is my formula for a sequence where n represents, and you start at 1 when you do this. So if I had my first term, a sub 1 would be 1 over 1 plus 1. A sub 2, my second term would be 2 over 2 plus 1. A3 would be 3 over 3 plus 1. A4 is 4 over 4 plus 1. And A5 is 5 over 5 plus 1. So my first 5 terms of the sequence could be these. So I'd write it as, this would be 1 over 2, 2 over 3, 3 over 4, 4 over 5, and this would be 5 over 6. And you can see a pattern going on here. I bet you could tell me the next pattern in here would be 6 over 7 if we had to. Right? The neat thing is if I give you this formula, I say, what is the 25th term of the sequence, a sub 25? You could tell me, well, it's going to be 25 over 25 plus 1, which is 26. You can tell me the pattern if I give you the formula. And kind of stuff related to sequences going on. Um, okay, so get this. Sometimes in sequences, you can recursively define them. So if you're into computer science, you might have heard this word. Recursive is the idea is that I'm going to use the previous answer as part of the next answer. So it's like, hey, if I have this formula right here. So if I say my first one's a sub 1 is 5 and I want to write the first 5 terms of the sequence. Well, this formula here says a sub k plus 1 is equal to 3 times a sub k plus 4. What this is saying is the next term is equal to 3 times the previous term plus 4. All right. So it's not just, oh, add 5 every time. It's, oh, maybe I'm going to do something else. Like, maybe, so it's not, or let me say this differently. This is defined in a way that I can just get the 20, I can tell you the 25th term. I don't need to know what the 24th term was because this is the formula I can follow. This is this is a different way of doing a formula for a sequence where it's telling you based off the previous term. So if you were doing this, your first term a sub 1 going to be 5. Your next term a sub 2 would be 3 times the previous one. So it's going to be 3 times a sub 1 plus 4, which is going to be 3 times 5 plus 4. So it's going to be 19. A sub 3 would be 3 times 19 plus 4. Going to be 47. No, it's going to be 57 plus 4, 61. A sub 4 would be 3 times 61 plus 4, which is going to be 183 plus 4, 187, and so on. Your a sub 5 would be 3 times 187 plus 4, which is going to be something gross. I don't know how to do this. So it's going to be 531 plus 4, which is going to be 535. So that might be how I do these kind of things recursively. All right. Um, I might ask you to write a definition. I kind of want to show this to you. You know what? It's even in the you have reference. So maybe I want to write the definition of a sequence. So let's say I take this same one. I want to write my formula for it. So your a sub k plus 1 is equal to something related to a sub k. Well, let's look at what's going on in this sequence. I'm going from 2 to negative 6 to 18 to negative 54 to 162. All right. How do I get, so maybe my first guess is, okay, I'm subtracting 8 this time. But then now I'm like adding 24. But now it looks like I subtracted like 18 plus 54 is subtract 72. This looks like a weird pattern. That doesn't make sense. What if it's a multiply pattern? You might go, oh, 2 times 6 times 3 is 6. Times number 3 is 18 times another 3. Okay. So it's like a 2 times 3 every time, right? You're timesing it by 3. So you might say, oh, my pattern is, well, okay, you're starting with a sub 1 is equal to 2, right? That's your initial one. Your pattern says, hey, I have to multiply by 3, so I go 3 times a sub k. Yep. So, oh, would it be negative 3? Yeah. So negative 3 will work, right? Yep, because you got that negative thing, and that'll make it work. There would be a recursively defined sequence. You know what's crazy? We can actually define things recursively, but we can write an expression for the nth term. What if I don't want to make it recursive? I can actually write this both ways. But that's, so we don't have to use this. How would I write this both ways? A sub n. So a neat thing with this, see how we're multiplying by 3 every time? we're going to get to this later in this lesson right now. We call that, it's something, spoilers, about a geometric series. And if, again, sometimes it assumes that you did something in Algebra 2 and you've heard of the word geometric series. Has anyone heard of geometric series before this class? I don't know. But we're multiplying by 3. I can actually write an expression for this since I start with 2. And I'm multiplying by 3 to a certain exponent, right? So we're going to say 3 to the n. But since we start with n equals 1, we're going to say 3 to the n minus 1. And then we have a negative in there. So actually, I think I can write this as negative 3 to the n minus 1. Now, I just want to show this to you. I'm not worried. I'm not going to ask you to come up with a bunch of formulas. But I can write this same one. So if I use this pattern, I started with n equals 1, I would get 2 for the first one. And then for the second one, I would get negative 6 because it'd be 2 times negative 3 to the 1 power. So this would work and this would work. We can write formulas both ways. So you might see recursively defined things. You might see, I think sometimes they call this explicitly defined. I don't know, but I don't have that word being used here. So I want to show that to you. You see that? All right. So here's another thing about sequences. We've talked about improper fractions converging or diverging. Sequences can also converge or diverge. Basically, it converges if it goes to a number. So here's the technical terms. If this a sub n is a sequence and the limit as you go to infinity goes to a number, we say the sequence converges. If it goes to infinity or like negative infinity, it keeps getting bigger and bigger forever, then it diverges or it gets smaller and smaller forever. So let's give you an example. I hate that example right here. If I want to make a series, 1, 1/2, 1/4, 1/8, etc. Right? And you could probably look at that pattern and say, oh, you're doubling the bottom every time, so 1/16, right? If you kept doubling, and what would be, and you go out to infinity terms, the bottom gets bigger and bigger and bigger. It's basically going to go out to 1 over infinity, which we know is 0. So we would say this sequence converges. Another sequence I can make converge is something very similar to this. Let's say I had the sequence, say I said 2 over 1. And then I went to 3 over 2. I went to 4 over 3. And then 5 over 4. And then 6 over 5. Right? My next one would be 7 over 6. You see, I have a pattern going on here. The question is, what would this go if you went out all the way to a value of, you can see the pattern here. We basically have a bigger number on top. We can say it's n plus 1 on top and n on bottom. If you took this as a limit of this pattern, n plus 1 over n, the limit as n goes to infinity of that, following L'Hopital's rule, would be 1. So something like this would converge to a number as well. But maybe if I had a pattern that just like doubled every time, it would not converge. An example of something that would not converge, I'm not using their examples as stuff. Let's say I had a different pattern. And let's say I just go 1 plus, what if I did not plus? 1, 3, 5, 7, 9. It's going up by 2 every time. But if you kept just adding 2 everything, you're going to go up to infinity. So we're going to be diverging here. That'd be example. So sometimes it matters if, for this point, I think this is the Khan Academy stuff, does it converge or diverge? All right. So if let's say I had these sequences here. I think this is, I'd have to look at this. Hold on. I'm going to finish this lesson one way or the other. So let's take these patterns. I want to ask if these converge or diverge. So you might look at this and go, well, I don't know. You can write out the patterns. It's 3 plus negative 1 to the n power. But you know what you do? You just got to do the limits. Then goes to infinity of 3 plus -1 to the n. That handwriting's awful. What's going on? Well, what's going to happen here? This -1 to the n part is just going to be like doing +1, -1, +1, -1. If I actually listed out these, I started with n equals 1 right here. I would have 3 minus 1, I'd have 2. Then I'd have 3 -1 squared. 3 plus 1 is 3, 2. Then it'd go to 4. Then it'd go to 3 minus 1 is 2. This pattern actually oscillates between 2 and 4. When we have an oscillating pattern like this would be diverge. So it's not just going to infinity or negative to infinity. If it oscillates between like some numbers, but it's not approaching anything, we also say diverge. Let's take this top one. So you can just do this as a limit problem. Limit of n squared over n. We can take our L'Hopital's rule. If you tried to plug in infinity, you'd get infinity over infinity. Let's L'Hopital's rule it. Derivative of the top is going to be 1 over n squared times 2n. And derivative of the bottom is 1. Kind of simplified this kind of stuff. You just get 2 over n. You'd get 2 over n. Be 2 over infinity, which would go 0. So we would actually converge here. And the limit would be converging to 0. So there you go. I'll stop right there for